Good morning, students. In this class, we are going to discuss about divide and conquer strategy. It is one of the algorithm design paradigms used to solve complex problems which are not easy to solve. The key idea in this divide and conquer strategy is if the problem is a complex one to solve it, then we divide it into subproblems. Even though the subproblems are also complex to solve, again we divide the subproblem into subproblems. In that way, we repeatedly perform the division operation and it divides the problem repeatedly into subproblems until the problem becomes a simple to solve. Once the subproblems are simple to solve, the subproblems are solved separately. After solving or after finding solution of the subproblems, combine the solutions of all the subproblems to obtain solution of the final problem. That is the key concept in divide and conquer strategy. So divide means divide the problem into subproblems. Conquer means solving. So solve the subproblem. If it is not possible to solve the problem as a single entity, then we divide the problem into subproblems. The control abstraction. Look into the control abstraction of divide and conquer problem. Here P is the given problem. First we verify if it is a small one, small to solve or easy to solve. Small of p determines whether the problem P is a small one or not. Small means easy to solve. If it is a small one, simply returns the solution. Else, that means otherwise, the problem is not a small problem, it is a large one, it is complex to solve. Then we divides the problem into smaller instances. So P1, P2 up to K. That means the problem P divides into K number of subproblems and apply divide and conquer on each subproblem if they are also large or complex to solve. Even though the problem P divides into subproblems P1, P2, P3 up to Pk, again we need to apply divide and conquer strategy on each of them when they are complex to solve to make them simple to solve. After divides and solve each subproblem, we use combine method, return combine. So combine means merge the solutions of subproblems to obtain the solution of the problem. After solving the subproblems P1, P2, P up to Pk, we merge or combine the solutions to obtain the solution of problem P. Its time complexity is g of n when n is the small one. G of n is a function. The time complexity is equal to g of n where n is a small one. Otherwise, the problem divides into k instances and each instance time complexity is T of n plus n1, T of n2, T of n3 up to T of nk plus f of n, where the subproblems are similar complexity can be represented by using the recurrence relation. The subproblems are similar, then we use the if in the if n is equal to 1, then its time complexity is T of 1. If n is greater than 1, then the problem divides into a number of problems and each problem size is n by b. Then the time complexity is a into T of n by b. So a represents the number of subproblems and n by b represents the size of each subproblem. One application or example for divide and conquer is binary search. We already know about a binary search strategy. Binary search is used to find the element index in the given array. Is it available in the array or not? Is it available in the list of elements or not? Search for the key element. If it is available, it returns index. If it is not available, it simply forwards the search up to all the elements are verified. For this binary search, the key constraint is the list of elements or array of elements must be in sorting order, that too in ascending order only. The list of elements must be passed in the ascending order. Okay, in this algorithm there are four parameters. A represents array of elements, I represents starting index of the array, J represents end or higher index of the array, higher index value, X represents the key element to be searched in the array A. If lower index and higher index value both are same, I is equal to j, that means the array have only one element, so that it is a simple problem. Verify the element is equals to x or not. If it is equals to x, then return the index value I. That means the element x is available in the array, found in the array at index I. If x is not equal to a of I, that means there is only one element and it is not equals to the element, key element x. It means the key element x is not available in the array. So return 0. 0 means the element is not in the array. Else, else means I is not equal to j. So lower index is not equals to higher index. That means the array have more than one element. Now the problem is complex one. So we need to divide the problem into subproblems. The problem divides into two subproblems based on the mid value. Mid is equal to I plus j divided by 2. So problem divides into two subproblems of equal sized. Two subproblems of equal sized. So n divides into two subproblems and each subproblem size is n by 2. So like that. So after division, after finding the mid value, first verify the key element x is equals to a of mid, then return the mid value as the index of key element in the array. If it is not equals to mid, again verifies x is less than mid element of the array. If x is less than mid element of the array, that means it is in the first half of the array because the elements are in sorting order. Then return or by again recursively call the set by setting lower index as I and higher index as mid minus 1. That means it is in the range of I to mid minus 1. If x is greater than a of mid, that means it is in the second half of the subproblem. So that again we call binary search using lower index as mid plus 1 and higher index as j. Here we take a simple example. There are a list of elements in ascending order 1, 3, 5, 7, 9, 11, 13. The key element need to be searched is sum 2. The key element is 2. First, it verifies the problem size lower index is 0 and higher index is 6. So I not equal to j. Lower index not equal to higher index. Then we calculate the mid value. Mid is equal to 3. So the element at index 3 is 6, 7. Now compare x is equal to 7. If it is true, it returns 7 and stop the search. If it is not equal to true, then expand the search either left side or right side. If it is less than 7, expand towards left. If it is greater than 7, expand towards right child. So in the left side, x is equal to 3. Again, verifies. Then after x is equal to 1 and 5. In the similar way, in the right side also, first it verifies x is equal to 11 because it is the mid element of right side sublist. If it is equal to 11, stop the search and return the index as 5. Otherwise, it continues the search. Left side is x is equal to 9 and right side x is equal to 13. So in this way, the search forwarded until all the elements are visited. Even though there is no matching element, then it returns there is no matching element. The time complexities of a binary search. Unsuccessful search, that means worst case. Worst case means even though we search entire list of elements, there is no key element. Such type of search is called worst case search. Best case means the middle element is the key element. It is the best one. It takes only one comparison. Whereas the worst comparison requires log n time complexity. So the time complexity, average case and worst case time complexity of binary search. If n is equal to 1, its time complexity is 1. If n is greater than 2, in each iteration based on the mid value, the problem divides into two subproblems and the size of each subproblem is n by 2. Okay, so now it is a recurrence relation. T of n is equal to T of n by 2. Here we doesn't consider the second half. In the binary search, we expand search either towards left or towards right, either first half or second half. But we need not to combine the solution of subproblems because The element is available in right side sublist or left side sublist. When the key element is found, we stop search. That is the solution. We need not to combine the solutions of subproblems to obtain the solution of main problem. That's why here we consider the time complexity when n is greater than 2, t of n by 2 only. We consider either left side or right side sublist. So upon substitution, t of n is equal to t of n by 2 plus 1. Next, t of n by 2 is equal to t of n by 4 plus 2. So, t of n by 2 power 2 plus 2. Next, again, t of n is equal to t of n by 2 power 3 plus 3. In that way, t of n is equal to t of n by 2 power I plus I. Let us assume that 2 power I is equal to n. Apply logarithm on both sides. Log 2 power I is equal to log n. So I is equal to log n. Substitute 2 power I as n and I is equal to log to n. So n by n, t of 1 plus log n. So t of 1 is equal to 1 because the best mid element, best case. So 1 plus log n. So here the time complexity is approximately equals to big O of log n or order of log n. It is the average case time complexity. In best case, it takes only 1. In the average and worst cases, its time complexity is order of n. Order of log n. That is the advantage of binary search. So it is about how to perform binary search on very large number of elements, very complex list using divide and conquer strategy. So thank you.